So, welcome back, everybody. Today is session 6 on our internship on machine learning used in biology, right? So, till yesterday, we have learned about some of the basic concepts around machine learning, right? So, we have learned about concepts like cross validation, supervised learning, unsupervised learning. We have learned about the bias variance trade off, etc., etc., right? So after that, yesterday we studied our first machine learning algorithm, which is linear regression, and we saw how using very cool and very clever mathematical techniques like gradient descent and optimization theory, we are kind of fitting the best possible line to our data wherein we are trying to predict a target or a dependent variable using one or more features or independent variables. Okay, so we saw how we exactly do that yesterday's class, and that is a regression setting. It is a regression problem where you're actually predicting a particular numerical value, or as we say in a more technical term, you predict a continuous variable. Okay, in today's lecture we will go through a classification problem, right? So in today's lecture, our focus will be on the algorithm which is known as logistic regression. Okay. So logistic regression is used to deal with classification problems, or in other words, we use it to predict discrete variables, right? Variables that come in frequency, right? For example, we saw that a setting where we are differentiating between healthy individuals versus diseased individuals, right? So we have two classes for our target. First class is healthy, the other class is diseased, right? So that is the kind of thing that we'll be dealing with today in today's class. Okay, so just like yesterday, we'll first go through the theory of logistic regression in as much detail as possible. I don't want to overwhelm you guys too much with the math again today. Since we did a lot of math yesterday, I want to go easy on you guys. And the math behind logistic regression is considerably more complicated than the math behind linear regression. So I won't burden you a lot with all of the math, but we will do some of the math to actually give you guys that intuition that I was talking about to help you understand how these things actually work in real life. Okay. So with that said, let us begin with our theory on logistic regression. Okay. So logistic regression is all about predicting whether something is true or false, right? As I said, it predicts a class and it does not predict a continuous variable, right? A continuous variable or a numerical variable is not predicted by logistic regression. Consider this, for example, right? On the x-axis, you have weight, and on the y-axis, you have whether these samples are obese or not obese. Okay, so this is something that looks like the job for a classification algorithm or something like logistic regression, where with respect to weight, we will use the weight as a feature to actually classify the samples into two classes, which is obese and is not obese. Okay, so this is something that looks like a problem for logistic regression. Now, also, in case of logistic regression, this is something which is very different for it from linear regression. In case of logistic regression, instead of fitting a straight line to the data, we fit kind of an S-shaped function to the data. This is known as the logistic function or the sigmoid function. Okay, this function is known as the logistic function or the sigmoid function, and it is an S-shaped function. Okay, so the beautiful thing about this function is that it confines the values, so the limits of this function are from 0 to 1, right? In math, right, or in basic mathematics, what other entity or what other quantity is confined between 0 and 1? Any guesses from anybody? Any guesses, people? So the sigmoid function always squeezes. So whatever you input to the sigmoid function, right, you get the answer always between 0 and 1. Okay. What other thing in math is always between 0 and 1? Or I should say, what other thing in math and statistics is always between 0 and 1? No, I'm not talking about a number. I'm talking about an entity, a concept. Any guesses? Probability. Yes. Very good, Sayyida. Probability is always going to be between 0 and 1. And therefore, the use of the sigmoid function basically tells you what? It tells you that logistic regression deals in probability, whereas linear regression was dealing with some continuous variable that can go from, that can practically be any value, basically, right? Logistic regression is something that deals in probability, so your predictions will always be between 0 and 1. Okay, now let us go back to the slides and see what exactly we do in logistic regression. Okay, so as you can see here, it fits such a S-shaped curve to the data, right? And these are your y-axis, where we have basically just discretized the y-axis and we have kept the two possible outcomes here. Okay, so this means that the curve tells us, which is exactly what I said, the probability that a mouse is obese based on its weight. Okay, so this y-axis is nothing but the probability of this mouse being obese given its weight. Okay, therefore the y-axis goes from 0 to 1. As you can see, there are two classes: the mouse is obese, the mouse is not obese, right? Ideally what we do is we choose one of the classes as our reference point, and all the probabilities are calculated based on that. For example, in this case, we have chosen obese as our reference point, and whenever we calculate the probabilities, whenever we say which is the probability, we say that the probability of this mouse being obese is being calculated. That is because obese is the one that is assigned the class 1, and not obese is the one which is assigned the class 0, right? If you think about it, why is not obese 0? Because when a sample is not obese, the probability of it being obese is 0. And why is obese 1? Because whenever a sample is obese, the probability of it being obese is 1. So that is the simple intuition behind 0 and 1 here. Okay, now let us consider this example, right? If this is the weight of a mouse, right, I can project this weight onto the sigmoid curve, onto this S-shaped curve, and I can figure out that for this mouse, which has a very high weight, there is a high probability that this mouse is obese, because the probability is going to lie somewhere near 1, right? This one, on the other hand, where the weight is somewhere in the middle, not too high, not too low, right? The When I project this weight onto the sigmoid curve, this comes out to be somewhere around the halfway point between is obese and not obese. So it is around zero point 0.5, or I can say that a mouse with a medium weight has a 50% chance that it will be obese. Lastly, if the weight is somewhere around here, right? If the weight is somewhere around here, that is very low weight, right? And I project it onto the sigmoid curve and I take it, I then project it onto the y-axis, I can clearly see that there is very less probability of the mouse being obese, because this is near 0, right? Therefore, a light mouse has a very less probability of actually being obese. And that kind of makes sense, right? Logically, if the mouse is heavier, it is more likely to be obese. If the mouse is lighter, it is very less likely to be obese. And if the weight is somewhere in the middle, there is almost an equal chance of it being obese or not obese, right? So this is how it logically makes sense. This is the intuition behind converting a discretized problem to some sort of a continuous problem. 0 to 1, if you're predicting a value between 0 and 1, you are still predicting a continuous variable. But remember, the outcome is always discrete. The outcome is always discrete. You always end up discretizing the outcome. And that is why this is a classification problem. But since you are predicting the probability, which is a continuous variable between 0 and 1, you still call it regression. Okay, that is exactly why you call it regression. Although this is a classification setting, since you end up predicting a continuous value between 0 and 1, you still call it a regression algorithm. Okay, so for example, if the probability of a mouse is obese is greater than 50%, right, then we can classify it as obese. Otherwise, we can classify it as not obese. This is the part that I was talking about when I say that we discretize the problem. Okay, if I have the weight somewhere here, that graph will coincide somewhere here, which would be around somewhere zero point 0.9 or zero point 0.8. So I have a zero point 0.9 probability that this particular mouse will be obese. So in my final results, I will classify this particular mouse as an obese mouse, right? So this is a cutoff that I have decided, that I will decide a cutoff of zero point 0.5. Anything with probability of greater than zero point 0.5 will be classified as obese. Anything with probability of being obese less than zero point 0.5 will be classified as not obese. That is something that I control by myself. Okay. With linear regression, we actually fit a line, right? We saw this. We saw exactly how to do this. And the method that we use is the least squares method, or we use the sum of squared errors, right? That is the same thing as the least squares, right? In logistic regression, however, we fit a S-shaped sigmoid curve, and therefore we cannot really use the same methodologies that we use for linear regression, because that does not really work here. Okay, so we use something known as maximum likelihood estimation. We will understand what maximum likelihood estimation in a little bit. Okay, but before we move on to understand stuff like maximum likelihood estimation and some of the basics of the math behind logistic regression, do people understand how we are discretizing this problem? Yes, it still is a continuous problem if you think about it, but at the end of the day, you end up actually predicting the probability, right? Okay, we have quite a few thumbs ups. Okay, then let us go ahead with our explanation of maximum likelihood estimation. Okay, so before that, just like a fair warning to all of you guys, that the math behind logistic regression, especially some of the concepts that we learn and a lot of the calculus that goes behind logistic regression, that is considerably more complicated. Okay, so we won't go into as much detail and do derivations like we did yesterday, right? That is not necessary for logistic regression, but we will take a sneak peek at it so that it kind of gives us a glimpse into the world of math and machine learning, and we understand how it actually works. Okay, and instead we what we'll do is we'll focus on the main aspects of logistic regression. Okay, the first of which is that the model fits the probability of your data belonging to a class. Okay, the first point that I need you guys to remember is that logistic regression does not directly predict classes. It does not directly predict that, oh, okay, this is obese or this is not obese. No, it predicts the probability of your sample belonging to a certain class. Okay, for example, it predicts the probability of your sample belonging to the obese class. Okay, it is you who then decide the class. Okay, you are the one who set a particular threshold for the probability. Today I showed you guys the example with zero point 0.5, right? We used zero point 0.5 as the threshold, and we said whatever has a probability greater than zero point 0.5, you please classify as is obese, and if the probability is less than zero point 0.5, you classify as is not obese, right? Tomorrow I can change this threshold if I want. I can keep the threshold at zero point 0.7. Okay, I can keep the threshold at zero point 0.7, and I can say that, okay, whatever is greater than zero point 0.7 I will classify as obese, and whatever is less than zero point 0.7 I will classify as not obese. I can keep the threshold at zero point 0.3 and say whatever is less than zero point 0.3 is not obese, and whatever is greater than zero point 0.3 is obese, right? So this is something that I control, and there is actually a way where you can identify the best possible threshold for your particular model and data, right? That method is known as a receiver operating characteristic curve, or the ROC curve. If you guys remember, we talked about it briefly when we talked about evaluation metrics in classification problems, right? So in classification problems, the ROC curve helps us decide the best possible threshold of our model. Okay, we will understand how ROC curve exactly does this a little bit later. Okay, when we have actually learned a few of these algorithms and we know how classification works very well, it will be easier for us to understand how we can use an ROC curve to actually decide the best possible threshold. Okay, but do remember this, that the threshold is something which is user defined and you can change it. And usually what people do is people try different thresholds until they get to the one that works the best for them. Okay. With that said, logistic regression obviously is very similar to linear regression in the sense that it also has parameters like theta. They are nothing but weights. If you think about it, we talked about these theta as parameters yesterday, right? In other words, or in machine learning lingo, I can also call them as weights. If you think about it, the expression was something along the lines of theta 1 x1 plus theta 2 x2 plus theta 3 x3 plus dot theta d xd, right? So what is theta doing here? For each and every x, rather for each and every feature, it is multiplying some quantity to it. So it is weighing it by some quantity, or it is a weighted quantity. Theta 1 x1, x1 is just the quantity by itself. Whenever you are multiplying theta 1 with x1, you are weighting you are weighting x1, right? You are increasing the weight of x1, you're increasing the contribution power of x1. Similarly, if you're multiplying some theta 2 to x2, you're increasing the contribution power of x2, right? Because that is what is giving you the final prediction, right? So therefore, these parameters which are theta, and this is exactly what is learned, we saw, right, how we actually optimize for theta. This is what learning is. Machine learning is all about learning all of these thetas. Machine learning helps us learn all of these thetas, and in common machine learning lingo, these thetas are also known as weights. And every independent variable, which is basically nothing but a feature, has an associated weight. Okay, and that kind of tells us the higher the weight is for a particular feature, it tells us how highly it is contributing towards your prediction. A feature which has a weight of 2 versus a feature which has a weight of 0.5 has a lot of difference in contribution. Okay, the feature which has a weight of 2 is contributing a lot more towards your specific prediction. Okay, is it clear to everybody? Shall we do a check, a group wise check? Yes. Let us quickly do a group wise check. I'll open the spreadsheet that I have of you guys. So group 1, Akshaya, Samiksha, Pratima, Siddharth, Uday. Thank you. Group 2, we have Varshini, Ananya. Thank you, Varshini. Ananya is not here. I thought I saw Ananya. Okay. Wahaj, Nawaz. Thank you, Nawaz. Wahaj and Ananya are not here with us today. Okay, Wahaj is not here. Ananya, I thought I saw. Okay, Ananya is also not here. No problem. Group 3, Krishna Karthik, Sudiksha, Manaswini, Lakshmi. Thank you. Hasini. Yes, Hasini, you are here, right? Did you understand? Hasini, is it clear for you? Okay, I think she might have some problem on her end. Okay, group 4, Hajra, Sayyeda, Sanjana. Thank you, Sayyeda. Nusaiba. Thank you, Nusaiba. Thank you, Hadi. I don't think we have Hajra. Oh, Hajra is also here. Hajra, did you get this part? Did you understand up to here? Thank you, Hajra. Okay, group 5, we have Lasya, Harshita, Ramya Shri. Thank you. Harshita, are you here? Harshita is not here, no problem. And Manaswin. We only have one Manaswin. Is it? Okay, no problem. Group 6, Haripriya, Tanmay. Thank you, Tanmay. Haripriya, Sara. Thank you, Sadia. Sara is not with us today. Okay, Sara is not with us. Soumya, Sai Krishna. You guys, Soumya and Sai Krishna are here? I don't think so. Okay, no problem. Group 7, Sahiti, Sadvedi. Thank you, Sadvedi. Sahiti, you're not here. Pallavi, Nikhil, quite a few people not here today. Maybe because it's Saturday, is it? Okay, group 8, Praneeth, Vidushi, Vedavati. Thank you, Vidushi. Shruti. Shruti, are you here? I don't think Shruti is here as well. Okay, now Shruti, you are here. Shruti, have you been able to understand up to here? Shivani, Sindhura. What about you guys? Shivani, not here. Sindhura also, I don't think I saw. Shruti, were you able to understand? Can you please give a confirmation? Okay, I guess they are having some problems on their end. No problem. Okay, so let us continue then. Since most of you have understood, let us go on with our lecture. Now, in order to understand maximum likelihood estimation and how it works, how exactly logistic regression kind of figures out the best possible sigmoid curve or the best possible S-shaped curve, right? We will take this example. Okay. So on the x-axis, you will have weight. This is your independent variable, right? This is your feature. Using weight, we will predict probability of being obese, which is 1, and probability of not being obese, which is 0. Basically, we'll predict the probability of being obese, right? The blue samples here are obese samples, and the red samples here are samples which are not obese, right? So this is the example that we'll be taking forward for now. Our goal here, obviously, is to draw the best fitting S-shaped curve or best fitting squiggle to the data. Okay, that is going to be our goal. Now, to solve this problem, right, the y-axis in logistic regression, which is this axis, is actually transformed from the probability of obesity to the log of odds of obesity. Okay, so just like the y-axis in linear regression, it can actually go from minus infinity to plus infinity. Right now, the y-axis in logistic regression is kind of confined, right? It is confined between 0 and 1. If we have to actually fit something, right, we have to do it in a regression setting wherein the y-axis has to be a continuous variable between minus and plus infinity, which is the case in linear regression, right? In linear regression, technically speaking, your y-axis can be any value between minus and plus infinity, right? It can be any value, right? So this is exactly how we are kind of mapping this problem onto the log of odds of obesity. We will see how we exactly do this. And we convert the y-axis from a probability axis to a log odds axis. Okay. The log of odds has a range between minus and plus infinity. So how do we exactly transform this y-axis to the log of odds of obesity scale, right? In order to do that, we use this formula, log of p divided by 1 minus p. Okay, this is known as the logit function, and the p here is nothing but the probability of the mouse being obese, or rather I should say the probability of your data point belonging to class 1. We have assigned class 1 as obese, right? So P here is the probability of your data point belonging to class 1, or in this case, P is the probability of the mouse being obese. Okay. So this is exactly how we convert it. Let us actually see this with a couple of examples. Right. This red line is with respect to P is equal to zero point 0.5. Right. If you actually plug in zero point 0.5 into this equation, right? If you actually plug in zero point 0.5 into this equation, what will you get? You will get zero point 0.5 divided by 1 minus zero point 0.5, which is zero point 0.5. So zero point 0.5 divided by zero point 0.5 is 1, and log of 1 is nothing but 0, right? So for the p equal to zero point 0.5 line here on the y-axis, you get this x-axis as the line on this log of odds graph, right? As the line. For example, if we put p is equal to 0.731, which is nothing but this red line, and if I plug it into this formula, what I will end up with is log of 2.717, which is nothing but is equal to 1. Okay. So a probability of 0.731 basically maps to 1 on this particular log odd scale, right? Similarly, a probability of 1, which is somewhere here, right? If I plug that in to the particular formula, I will get what? Log of 1 by 0, right? You cannot technically divide by 0, right? So instead what you can do is you can do log of 1 minus log 0. That is absolutely possible, right? So log 1 is 0, that is fine, right? But log 0 is defined as negative infinity. If you guys remember, log 0 is defined as negative infinity. So something minus negative infinity will give me what? Positive infinity. Anything, if I remove negative infinity from it, I will be left with positive infinity. So therefore, a p or a probability value of 1, which is the peak, which is the maximum possible value on the probability axis, translates to the maximum possible value on the log of odds axis, which is plus infinity or positive infinity, right? Which is plus infinity or positive infinity, right? So this means that the original samples, which were actually obese, which we had marked as obese in the probability setting right here, right? They actually map to the plus infinity line on the log of odds scale. Okay, this is where all these samples will lie. Very similarly, all the region between zero point 0.5 and 0 will map to the region between 0 and minus infinity on the negative side, right? 0 and minus infinity, right? So basically, how did we go ahead and convert this probability scale to the log odd scale? We use something called the logit function, which is nothing but log of p divided by 1 minus p, and we do it for each and every possible value of p here, and we kind of come up with this scale. Okay. And similarly, all these samples which had a probability of being obese as 0 will coincide to a log of odds of obesity as minus infinity, and therefore will decide here. So all the obese samples are now on plus infinity, while all the non-obese samples are now on minus infinity, and this is on the log of odd scale, or in other words, we also call it as the log odd scale. Okay. Do people understand till here? Can I get a thumbs up if you guys understood the transformation? Okay, 3, 4, 5, 6. Others? 7, 8. Come on, 2 more. 9. Thank you. One more, and then we will go ahead. Everybody understood? No more people? So I think only 9 of you are actually actively attending. The rest have just joined and gone back to sleep. I think that's what's happened here. Okay, no worries. You're lucky you guys have recordings. When we learned this in class, if we missed class, it was gone. We never got to circle back with the professors and they repeat this stuff. Never happened. Okay. So anyway, once we have actually stretched this, do we have a question? Anything coming in between zero point 0.5 to 1 maps on the positive in the log scale. Correct. Yes. Anything that comes with, and those are the examples we discussed, right? If you take a look at these examples, right, this is a positive value. This is between 0.5 and 1, right? So this comes to about 1 on the log scale, log of odd scale actually. Okay. Is that clear, Hadi? Okay. Okay. So now that we have actually successfully stretched this axis onto the log of odds axis, right? We are at a place where we can actually try and figure out how to fit a line like this to this particular data that we have. Okay. So first of all, let us assume that we, just like linear regression, we start with a random line, a random straight line. Now, if you think about it, the problem looks a lot more like a linear regression problem, right? Because now the scale goes from minus infinity to plus infinity. We have data points, right? So we have both, we have two continuous variables per se, right? So the problem has now started to look a lot like the linear regression problem that we did yesterday, right? So in the linear regression problem, if you guys remember, we start with a random line, right? A random straight line which has some slope and some intercept. Okay, and then we go on and optimize it. So let us do the same thing here as well. Let us start with this random line. Okay, now what did we do in linear regression yesterday as well? We calculated residuals, right? So we can calculate these residuals, right? But there is a catch here. The residuals, or I should say the distance from the data points to the line, will be equal to either positive infinity or negative infinity, because the data points themselves are at positive infinity or negative infinity, right? Here is the roadblock. Since the data points, since the residual values are positive infinity and negative infinity, it is not practically possible for us to follow the same route that we followed yesterday, figure out the sum of squares errors, which will be positive infinity and negative infinity, by the way, take their derivatives and then figure out how to optimize it. It won't be possible because the residuals themselves are negative and positive infinity. This is exactly why, even after converting the problem to a pseudo regression setting, right? This is not true regression. This is a pseudo regression setting, right? So even after converting the problem to a pseudo regression setting, we cannot use methods like the sum of square errors or least squares to find the best fitting line. Instead, we have to use other methods, something along the lines of maximum likelihood estimation. Okay, so that is what we are going to be doing now. So the first thing, in order to perform maximum likelihood estimation, is for us to project the data onto this line. Okay, so we project the data onto this line, and if I actually project the data onto this line, each point is projected onto the line. What will I do? I will end up with having a log of odds value for that particular data point. I will end up having a log of odds value, and that is exactly what I want here. Now, for example, for this particular data point, for this particular data point, right, I have projected it onto the line, and then I drop a perpendicular onto the y-axis, and I see that the log of odds here is 1.4. It should be minus 1.4. Okay, the log of odds here is minus 1.4. This is a typo, it should be minus 1.4. Okay, so just like that, for all of these data points, we figure out the log of odds value for these particular data points. Okay, then what do? We transform these log of odds values to candidate probabilities using this formula. Okay, and that is actually what is going to give us this sigmoid curve. So basically, if you think about it, this is nothing but the opposite of going this way. We first went from the sigmoid curve to a straight line, right? Then now we are going from the straight line to the sigmoid curve, right? Since we had projected the data points onto the straight line, when we take it back to the sigmoid curve, our points will be projected onto the sigmoid curve or the S-shaped curve. Okay. And the formula that actually helps us do this transformation back from log odds to the probability is known as the sigmoid function. This particular formula is known as the sigmoid function, and this is exactly the formula that converts everything and squeezes them between 0 and 1. Okay, this is that formula. If you think about it, this is nothing but going from this is what this is going from your probability scale to the log of odd scale. That is what this is, right? Now if you exponentiate both sides by e, right, what will you get? You will get p divided by 1 minus p on the LHS and e raised to the power of log of odds, right? Now you can obviously you can take this 1 minus p to this side, right, and you will get p is equal to 1 minus p times e to the power of log odds, right? Now what can you do? You can multiply 1 minus p and e of log to the odds, right? You can multiply this. So you will get what? E to the power of log to the odds, log odds, minus p times e to the power of log odds. This is what you get, right? Now you can take this back to the LHS, p plus p to the pe to the power of log of odds, which is equal to e to the power of log of odds. Makes sense, right? Now all you have to do is take p common out of both of these. So you will have 1 plus e to the power log of odds is equal to e to the power log of odds. Now all you have to do is take this back. So this is multiplied. This will go into the denominator here. So you end up with p, which is equal to e to the power log of odds divided by 1 plus e to the power log of odds. So these two formulas, the logit function and the sigmoid function, are nothing but two sides of the same coin. The logit function allows you to go from the probability scale to the particular log odd scale, and the sigmoid function allows you to go from the log odd scale back to the probability scale. Do people understand this math? Yes. Can we go group wise one more time for this? Group 1, Akshay, Samiksha, Pratima, Siddharth, and Uday. Uday has given. Thank you. Group 2, Varshini, Ananya, Wahaj, Nawaz. Okay, only Nawaz. So group Nawaz, you are the only one from group 2, is it today? Can you please confirm once?
No, sir, I think Varshini is here.
Varshini, have you been able to understand? Can you please confirm? You can write in the chat if your reactions or your mic is not working. Varshini, can you please confirm?
Suryadeep, let's proceed.
Okay, okay. Group 3, Krishna Karthik, Sudiksha, Manaswini, Hasini, and Lakshmi. Thank you. Group 4, we have Hajra, Sayyida, thank you, Sanjana, Nuseba, thank you, and Hadia. Have you understood, Hadia? Did you give a thumbs up? Okay, thank you. Group 5, Lasya, Harshita, Ramya Shri, Manaswin. Yes, do people understand? Thank you. Group 7, Sahiti, Sadvedi, thank you. Pallavi and Nikhil, I don't think you guys were here last time, but Pallavi and Nikhil, are you guys here now?
Always group 7 and 8 not attending. Survey, if possible, please give me an update in WhatsApp what's happening with your group. I don't think so. Most of you are attending it.
Okay, group 8, Praneeth, Vidushi, you guys are not here. Vedavati, you are also not here. Okay, Vidushi is here. Thank you. Vedavati is here. Thank you. Shruti, you were here. I saw. Okay, no response. Shivani, and Sindhura. Neither
Pranit
of
is
not.
also here. Pranit, any update?
Have you been able to understand, Praneeth, up to this part? Okay. You give a thumbs up. Okay. Uh, Shruti is not here, no, Bhavani? I
Yes, Shruti. No, no, Shruti is here.
Shruti is
Shruti,
here. Shruti,
she's
can you please confirm if you have been able to understand till here?
Shruti and Varshini are physically here. Let's continue, Pranit.
Yeah, okay, let's continue. Okay, no problem. Okay, so now we understand how the to and fro transformation works in these scenarios, right? And this is key to performing logistic regression. Okay, because by now, I don't know if you would have guessed it, or some intuition would have told you that what we will be doing is we will be trying a lot of these candidate lines, right? Projecting the data points onto these lines, calculating log odds, converting it back to the sigmoid, and then actually figuring out which one fits our data best. Okay, so there will be a lot of to and fro basically. Okay, just to give you guys an example to actually show you guys that this actually works, right? For example, for this data point, we can substitute minus 2.1 into the log of odds here. And if we actually do this, you can do the math at home for all of you who are trying to follow properly. You can do the math by yourself at home. And this will actually give you a probability value of zero point 0.1. Okay. So this will give you a probability value of zero point 0.1. And you can actually do this for all of these points. And what you will end up with is something like this. You will end up with something like this, which fits this particular sigmoid curve. Okay, so you have these particular points on the sigmoid curve. Now we know which ones are obese and which ones are not obese, right? This is the part where we know it is a supervised learning setting, remember? So we know which ones are truly obese, which ones are truly not obese. So we can use the observed status to calculate their likelihood or probability given the shape of the squiggly line. Okay, so we'll start by calculating the likelihood of the obese mice given the shape of this particular squiggle. Okay, so the likelihood that this particular mouse, for example, is obese given the shape of this particular squiggle that we got from the initial straight line in the log odd scale, right, is basically nothing but its corresponding value on the y-axis here, right? That comes out to be somewhere around 0.49, right? In other words, the likelihood that this particular mouse is obese given the shape of the squiggle is the same as our predicted probability. This is the probability that we are predicting, right? For this particular sample, our model, which came from this straight line, has predicted that this particular sample has a probability of 0.49 of being obese. Okay, and that is nothing but our likelihood of this mouse being obese given the shape of our sigmoid curve. Okay, so similarly, I can calculate the likelihoods of all the other blue data points or the obese data points. And for the sake of this example, let us say that the probabilities or the likelihoods are 0.91, 0.91, and 0.92. Okay. So we have these particular values now in mind. Do we have a question in the chat? Until now, there's network issue on my side. Okay, no problem. No problem, Varshini. If you have any questions, please feel free to raise your hand and we can address them. Okay. If even if you can't hear something due to network issues, you can let me know. We can repeat it maybe if there is time. Okay. 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 So these are the likelihoods that we have calculated from this particular sigmoid curve that we got. Okay. These are only for the obese mice. Now, the likelihood of our data given the squiggle is given by a product of all these likelihoods. Okay, so we have to multiply all these likelihoods. So let us keep it aside for now. We know these likelihoods and we have calculated them for all these blue data points. Okay, now we can do the same about the not obese class, right? We can do the same for the red data points. Now the probability that this particular sample is obese is zero point 0.9. Can you see? Therefore, if the probability that this particular mouse is obese is zero point 0.9, the probability that this mouse is not obese will be 1 minus zero point 0.9. Right? Makes sense logically? So because why? Because the y-axis is your probability of the mouse being obese. It is not the probability of your mouse being not obese. Rather, it is the probability of your mouse being obese, because obese is the class we have defined as class 1, right? So the probability that this mouse is not obese will be 1 minus zero point 0.9 or zero point 0.1, right? So now I can do the same for all the other data points here, right? The probabilities that all of these mice are obese are both 0.1 for at least these two data points. The probability that these two mice are obese is very low. It is very near zero, somewhere around 0.01. So the probability and therefore the likelihood that they are not obese is nothing but 1 minus 0.01, which is what? 0.99, right? So this is how we calculate the likelihood of this particular data, which are all the data points which are not obese, right? Now we can include that into our calculation, right? So the likelihood of this particular data, wherein we have obese as well as non-obese samples, is given by the product of all the likelihoods. Okay. Now, although it is possible to calculate the likelihood as the product of individual likelihoods, right? Usually statisticians or data scientists, etc., they prefer to calculate something called the log of the likelihood instead, right? In both ways, it is absolutely fine, because whichever particular sigmoid function or whichever S-shaped curve maximizes the likelihood also maximizes the log likelihood. Okay, if you guys remember, the technique that we are using is known as maximum likelihood estimation. So our goal here is to maximize this likelihood. Okay, so basically, if you actually maximize the log likelihood, it kind of, the math kind of becomes easier for you. Okay. That is why people prefer, or statisticians prefer, to use log likelihood instead of likelihood. And that is nothing but this, right? Whenever you go from the normal scale to the log scale, products become sums, right? And doing a sum is much easier than doing a product, both for a computer as well as for you by hand, right? So therefore, people usually end up using the log of likelihood of the data given the particular sigmoid shape or squiggle. Okay. Now, if you guys remember something that I said yesterday, that in all of machine learning, we are basically solving an optimization problem, right? Yesterday, we were planning to minimize the cost function, right, in linear regression. Today, with respect to logistic regression, our goal is to maximize this log likelihood. Okay, our goal is to maximize this log likelihood. So I can very easily calculate this, right? If you guys go ahead and calculate this, you can as well. Okay. But the answer is going to be somewhere around minus 3.77. So for this particular squiggle, right, that came from this particular straight line, right, you got a log likelihood as minus 3.77. Okay. Now we can rotate the line a little bit, right? So this is another candidate line. All we have done is rotated the line a little bit. So we have changed the slope and intercept basically. That's it, right? And just like we did in the previous iteration, we can again calculate its log likelihood. We first project the data onto the line, right? Then we convert the data back to the sigmoid curve. using this particular formula. Then we again calculate the likelihood values for all of these, and we can get the log likelihood of this particular sigmoid curve, right? If you guys go ahead and do this calculation again, whenever you have some time, you can check this out. What you will get is a log likelihood value of minus 4.15, right? So this clearly tells us that this line is not as good as the previous line. The previous line gave us a log likelihood value of minus 3.77. This is greater than minus 4.15, right? So this guy is not as good. This is worse. This particular sigmoid curve is worse. Okay. Now, the beautiful thing to note here is that the algorithm that actually finds this line. So what do we do at the end of the day? We keep on rotating these lines, right? We keep on rotating and changing the slope and intercept of this line in the log likelihood scale, and we keep on calculating in the log odd scale, sorry, and we keep on calculating the log likelihood of the squiggle given the data, right? So we keep on doing this until and unless we reach at a log likelihood which is the maximum possible log likelihood from this particular data point. Okay, and there is actually an algorithm to do that. The algorithm that finds this line with the maximum likelihood, right, what it does is each time it rotates the line, right, it does not blindly do trial and error. Okay, each time it ends up rotating the line a little bit, right, it makes sure that there is an increase in the log likelihood. Okay, so naturally, if every time you are getting a small increase in the log likelihood, right, you can actually fit the most perfect line with the maximum log likelihood after a few optimal rotations. Okay, and that is what this algorithm is trained to do. This algorithm is written to do that. Okay, it does not randomly try different slopes and different intercepts. It figures out different slopes and different intercepts that will actually make the log likelihood better. Okay, and this is actually done. So we talked about gradient descent yesterday. This is actually done using something known as gradient ascent. Okay, this is actually done using something known as gradient ascent, and that is not something that we will do in the math. We will not do the derivation of gradient ascent with respect to all of these log and log likelihood formulas, because it is quite complicated. I don't really want to get that much into detail for you guys, because at the end of the day, as long as you have the basic idea how it works, you should be good, because your goal is to build the models and interpret the models. Okay, so too much depth is not really necessary, but yeah, it is important for you guys to actually know this in order to internalize the fact that you are transforming this guy to a regression problem, then again turning it back to a classification problem. That is the crux behind all of this. Okay, so this is what there is for logistic regression with respect to theory. Finally, what we do is we kind of try different straight lines and figure out which one gives us the best squiggle by actually calculating the log likelihood. Whichever gives us the maximum log likelihood, we end up keeping that. Okay, and I kind of have a visualization for you guys to actually see this. Just check this out. Okay, this is actually how it works. Okay, so you have on the right hand side, as you can see, you have this. I will play this video again. On the right hand side, there is this is the straight line on the minus infinity to plus infinity scale, and similarly you have on the left hand side, just wait a sec, you have the corresponding sigmoid function. Okay, you have the corresponding sigmoid function. Okay, so you guys can check out this video. It is linked here as well as here. Okay, and obviously you guys can also, I have credited this person here. He is one of my favorite teachers. Okay, so this is the channel of somebody known as Professor Josh Starmer. Okay, he runs this channel called StatQuest. He himself is a geneticist. Okay, and he teaches machine learning. He teaches data science and statistics to everybody, basically. So you guys can check out his channel. Most of my lectures are inspired from him. So yeah, you can check out these channels as well. But yeah, with respect to logistic regression, this is what I have for theory as of now. As I said, the math is way more complicated than linear regression. So let's not go into there. But I hope you guys actually got the idea and the intuition behind logistic regression now and are convinced how, although we call it regression, it still is finally a classification problem. Okay. So I will do one more check with respect to the groups. Now that we have come to the end of the theory part, after this, we will start with our lab. Okay. So group one, can I have a thumbs up if you have understood? Akshaya, Samiksha, Siddharth, thank you. Uday, thank you. Pratima, okay.
I have a question.
Yes, Pratima, you have a question.
Why
Go
is
ahead.
it better to do regression instead of classification if the goal is to still classify, right?
So let me ask you this. You you saw the regression problem that we solved yesterday, right?
Yeah,
So that solves for a continuous variable, correct?
yeah,
There is no objective way for you to actually get to a discrete variable using such mathematical variation, using such mathematical tools. Okay, there is no mathematical tool available for you to directly give you a 0 or a 1 as an outcome. Okay, at the end of the day, if you think about it, all of these algorithms are optimization problems. Whenever you talk about optimization problems, right, you are optimizing towards something. If you have to go from 0 to 1, right, you first go from 0 to point 0.1, then you maybe go to 0.17, then you go to 0.23. Like that, you take small steps towards your goal, right? As soon as this concept comes in where you are taking small steps towards your goal, you have to work in terms of a continuous variable. And whenever you have to work in terms of a continuous variable, you have to take the help of concepts which help us in actually regression. Does that make sense to you, Pratima?
yeah, okay.
Yeah, that is why so in logistic regression, we end up regressing, or we end up predicting the probability, which is a continuous variable, right? That is why we have to take the help of the log odd scale and convert it to a regression problem. Okay. Although the final goal is classification and we are doing the classification, actually you as a user is the person who is doing the classification when you set that threshold of 0.5 or 0.7 or zero point 0.3. Okay, like we discussed. Okay, any other questions? Pratima, you have any more questions?
No, sir, but if I do, I'll let you know, sir.
Sure. Okay, thank you. So group 2, Varshini, Ananya, Wahaj, and Nawaz. Okay, Varshini and Nawaz, thank you. Others, I'm not sure. Ananya, I thought I saw you here, no problem. Group 3, Krishna, Sudiksha, thank you. Manaswini, Hasini, and Lakshmi. Thank you, Manaswini. Thank you. Group 4, Hajra, Sayyeda, Sanjana, Hadi, thank you. Nusaiba, we have Nusaiba here. Okay, no worries. But Nusaiba was here, right? Okay, no problem. Group 5, Lasya, Harshita, Ramya Shri, Manaswin. Okay, group 6, we have Haripriya, Tanmay, Sara, Soumya, Sai Krishna, and Sadhya. Are you guys here? Okay. Group 7, we have Sahiti, Sadvedi, Pallavi, and Nikhil. Okay, only two of you, no problem. Group 8, Praneeth, Vidushi, Thank you. Vedavati, Shruti, Shivani, Sindhura. Okay, I guess Shivani and Sindhura are not here. Uh, is
Sorry,
anybody
that
trying to speak?
same
Yeah.
vacation
Yes,
period, and
Bhavani.
most of them are traveling at the moment, so they couldn't
Oh,
attend the session.
okay, okay, okay. No problem.
Yeah,
No
hopefully
problem.
might cope up with the recordings.
Yeah, yeah, yeah. They should be able to. No problem. Okay, guys. So with that, we have now understood the theory behind logistic regression and how we use logistic regression to classify samples, or rather, I should say, how we use logistic regression to predict the probability of samples belonging to a particular class, right? And based on that, we can manually perform the classification. Okay. So that is the theory. Now, for the lab, what I want you guys to do is, as I have already mentioned, you guys go into the drive folder, right? There will be two folders here, scripts and data. Inside scripts, you will have this particular .py or Python file, right? Session 6 logistic regression.py. Go ahead, download it and place it in the folder, which is the PyCharm projects folder, right? Similarly, you guys should place this inside the data folder. You guys should place this dataset diabetes.csv. Into this you can place anywhere, but just make sure you know where you are placing this file. Okay. Just know the path where you are placing this file. Okay. Once you have done these two, go ahead and open PyCharm and open up the logistic regression script in front of you. Okay. Once you have done that, please give us a thumbs up here in the window. Okay. Ramya, you have done that. Others, I'll give you maybe a couple of minutes. Please do this. You can keep it anywhere you like. Just remember the path. Okay, just know where it is. For it to be easy with you, you can keep it in the same folder as the PyCharm projects folder. Okay, but just remember the path. Okay, so has everybody been able to download the script and the data? Can we have a thumbs up? Okay, quite a few of you. Others? Thank you. Okay, now that most of you have done that, okay, we will start with the execution of the script. Okay, and in today's script we will go into EDA into we'll do some EDA in a bit more detail today. Okay, and we will actually understand some more things that we can do with our data. Okay, so go ahead and open the script. Okay, and we have this here, then we will run it. So first of all, as is with every Python script, the first section is nothing but an import section where you import every last library or module that you need for your data. Okay, so this is what I have done here. Okay, I have done all these imports. Don't worry if some of these are actually grayed out here. That is because some of the code I have commented here, we will uncomment these parts and we will run them. Okay, no worries. So once you have done all of this, the only new one that you see here is import OS. So this allows you to perform some um, OS level commands and operations. Okay, nothing too major for you guys. Just know that that is what it does. Apart from that, we have also used something known as resample. Okay, you'll see what this does in a bit. Okay, and we have imported the logistic regression function from the linear models library. Okay, so the linear regression, logistic regression, both are part of the linear models library. Although logistic regression ends up fitting a sigmoid curve and not a line, in the log odds situation, right, when we are in the log odds scale, it does fit a line for the data, right? That is why it falls under linear models. Okay, so and from the metrics library of scikit-learn, we have imported all of these necessary metrics, right? So we have imported accuracy score, confusion matrix, precision score, and F1 score. Okay. So now that we have that, the first thing that we will do is just like in R, where you set the working directory using setwd, here also you can set the directory using the command os.chdir. os.chdir. Okay, and you can set it to the path where your data set is present. For me, this is the path where the data set is present. You can set it to that path. Okay, so go ahead and edit this for you guys and set it to the path where the data set is present. Okay, so I'll give you guys again 2 minutes to check out the path, copy it and paste it. Make sure that you have forward slashes here. When you paste it by default, it will give you backward slashes, but make sure you have forward slashes. You need forward slashes. Okay, you guys can take a couple of minutes, but not too much time. Okay. Okay, I hope all of you have done this, right? Can I get a thumbs up if people have done this? Change the path. Latima, thank you. Others? Okay, we have quite a few thumbs ups. Let us go ahead. Okay. Now, what we will do is just like every other Python script in PyCharm, we'll set a breakpoint here and we'll click on the debug button. Okay. Once we have clicked on the debug button, let's give it some time to process these previous lines. Okay. Give it some time. Yes. So now if I go back to the console, I have this Python console ready here. Now I can click on step over. As you can see, this has now set my working directory, and now I will load the data using pandas. Okay, so this is not something we discussed yesterday. Yesterday we loaded the data directly from the scikit-learn library only, because the scikit-learn library also comes with some data, so we did that. This is the one that you will be using more commonly. Okay, guys, just give me 1 second. Okay, just 1 second. Yeah, so sorry for that. I'll share my screen again. Okay. Yeah. So yesterday we looked at how we can actually load the data using the scikit-learn library. Okay. That actually fetches the data from the internet the first time when you run it, and then stores it within its own library package. So that is not something that you guys will be doing most of the time. Most of the time you guys will be doing it like this, where you use pandas. Okay. So pandas has a function called the underscore CSV function, and you can actually use that particular function to load the data. So if I go ahead and run this line, you can see that it has now loaded the data into this data frame diabetes underscore PDF. Now this worked with only the name of the file because I have set the working directory here. So it looked for this file inside this working directory. Okay. If I wouldn't have set the working directory here, what I would have to do is give this entire path here as a string. Okay, that is how it usually works. Okay, so now that you can see that this data set has been loaded, you can actually open it up and we can actually take a look at the data. Okay, let us actually take a look at the data. Actually, I want to check out one thing. For some of you, there might be a data panel here. Okay, that will also help you figure out the data. For some reason, that is not coming up for me here. Maybe it was a feature of the free PyCharm version. So you guys would have installed it just a while back, right? So you guys still might have that. But anyway, we can inspect the data from here. Okay. So as you can see, this is your data set. Okay. Your target variable is this, which is outcome, obviously. And you can see that there are ones and zeros here. Okay. So this is your target variable. All the rest of them are nothing but features. Okay, so you have features like the number of pregnancies, the glucose level, the blood glucose level, the blood pressure, skin thickness, insulin levels, BMI, right? All of these are features. You also have age and diabetes pedigree function. Okay, so these are going to be your independent variables or features which are going to help you predict this particular outcome. Okay, so once you have this data set ready, what you can do is you can do some basic EDA, right? So let us go ahead and try and do some basic EDA. The first thing, we can print the first 5 rows, right? We can print the first 5 rows and take a sneak peek at the data, right? Next, we can print what are the columns of the data set to actually figure out the features and the particular target. Okay, as you can see, these are all the columns. Next, we can print as simply the shape of the data set. So now we can see that this data set has 768 samples and 9 columns or 9 rows. So out of the 9 rows, obviously, one will be your target and the rest 8 are going to be your features. So right now you have 8 features here. Okay. Is anybody trying to say something? Okay. So this line, if you guys remember from our lecture on pandas, is to figure out how many null values or missing values are there in our data, right? So this guy first figures out every time there is a null value, it counts it, and this guy basically sums all of those counts. Okay. So if we go ahead and run this line, you can see for each of these columns, I can get to know whether there are actually any missing values. As you can see, for all of them, we see zeros. So we know that none of the columns have missing values. So that is good for us. Okay. Now let us actually do some basic plots. My goodness. Now let us actually do some basic plots for us to actually understand and do some EDA. Okay. I will go ahead and stop this run here because I want to go ahead and uncomment this. So in order to uncomment this part, what I want you guys to do is you can select this entire part, right? So select it from line 24 till line 35 and then press control question mark. Control question mark. Yes. Okay. So then this line, this part would have been uncommented. Okay. Similarly, I want you guys to do it for lines starting from 40 till 59. You select it and then press control question mark. That will uncomment that particular line. Okay. So let us actually try and do a few of these plots and understand what exactly this thing does. Okay. So I'll put a breakpoint here, remove this previous breakpoint, and then click on debug. So now again it will run. Just give it a minute. Yeah, it has run till here. I will go ahead and print this. It is null. Now I will figure out the correlation heat map. So this is something we have already done yesterday, right? So we know how this is and what this looks like. Okay. So just give it a bit and show. So here I can see the correlation heat map. Okay. So in this code here, you would have seen that there are two new kind of parameters, which is the Vmin and the Vmax. Okay. So these are nothing but the parameter that actually kind of normalizes these values. Okay. So if you don't give Vmin and Vmax, uh, this value is not normalized. As you can see right now, the values are normalized and are between -1 and 1. Okay. So that is what the Vmin and Vmax ends up doing. Okay. So from this feature correlation heat map, actually, you can infer quite a bit. Okay. If you see here, age has quite a bit of a positive correlation with respect to pregnancies, right? Glucose has quite a bit of a positive correlation with respect to outcome, which is something that you expect. Somebody with general high blood glucose level, I mean, that is literally the definition of diabetes, right? So that kind of makes sense, right? Some other notable high positive correlations would be this guy, insulin with respect to skin thickness. Maybe there is some relation, we don't know. And then again, we have 0.39 here for BMI with respect to skin thickness. Again, something to take note of. Okay. However, personally, I don't think all these correlations are too high for you to actually um, keep one of these variables and remove the other. Okay, the maximum that you see here is 0.54. Okay, unless and until you see correlations north of 0.85, you don't see correlations greater than 0.85 between any two variables, it is advisable to keep both of them. Okay, so since now that this is done, I will close this. Okay, now what we will do is we'll do a simple frequency plot of the two outcomes. Okay, so as you can see here, okay, so this came up automatically because I closed that previous plot. I'll quickly run this. Okay, you guys can also run it. Yeah, so this is the frequency plot. As you can see, this is nothing but a bar chart. There are two possible outcomes, 0 and 1, right? So 0 is for people who don't have diabetes and 1 is for people who have diabetes. Okay, as you can see, these are not balanced. Okay, so this is a situation where we are working with imbalanced classes, so we might have to use techniques to actually fill these balances. We might have to do some resampling, we might have to do some downsampling or some upsampling. Okay, but as you can see, the number of healthy individuals is almost 500, whereas the number of diabetes individuals is around 250. Okay, so this is the frequency plot. Now here is the beautiful part where we will be doing some histograms and some probability density distributions. Okay, so what I will do is I will first extract the features. Okay, so in order to extract the features, what I am doing is I am creating a list called features. Okay, how am I creating it? I am putting it inside the square brackets that automatically denotes that this is a list, right? And inside it, I am putting a for loop. I am saying for column in diabetes df dot columns, right? And inside the for loop, I am putting an if condition, right? So this is if call is not equal to outcome. So what will this do? This will basically keep all those columns which are not outcome. Okay, and it will pass it on as a part of this list. So the way I have written here, this is something known as a list comprehension, and this is available in Python. So how you read it is that in features include call, right? But what is the condition for you to include call? For call in the diabetes df columns, if call is not equal to outcome, that is what is going to happen here. So this is kind of like a one liner list comprehension. You could have written 4 or 5 lines for the same thing, right? And it would work the same. Okay, so this is just a one line, it's just a shortcut that I wanted to show you guys. Okay, as you can see here, once I have run this line, this list is nothing but a list of all the other columns which are features, right? Which are not our target or not the outcome column. Okay. Now we will do a loop through the features, and for each one of these features, for each one of these columns, we will do first a histogram by the outcome. Okay. And then we will do a box plot and a violin plot split by the outcome. Okay. So here, since we have two separate outcomes, we can actually do these plots. Okay. So let us go ahead and do this one by one. Okay. For the first one, let me run this. So I will first define the figure, right? Then we give it that, okay, this is going to be your plot. So this is the first plot. This is the hist plot. The data is going to be diabetes data frame. This is the entire data that we are giving it, right? Your x-axis will be columns. Your y-axis will be outcome, right? Your hue will be outcome. So basically, it's a histogram, right? It's a histogram and then a probability distribution function over the histogram, basically, right? That is what this KDE is. When I say that KDE is equal to true, okay, KDE is nothing but the this thing, the density, the probability density, basically. Okay, so we in technical terms we call it as the kernel density, right? But it is nothing but the probability density. Okay, so bins is nothing but the difference at which you want each bar in your histogram, right? And then the element and stat, you set it to step and density. So when you set the element to step, it basically see here, it basically either you want steps or do you want bars, like that. And the stat, that is the statistic that you want to calculate, is the probability density. Okay, so if you go ahead and run this guy, and then the title, the X label and the Y label. Okay, then we will also do the violin and the box plot. Okay, so we'll go ahead and do this again. For the box plot, the data is going to be our diabetes data frame. Your x-axis will be your outcome. Your y-axis will be the call that you have selected here right now. What is call? Call is pregnancies. Okay, you can hover over call and figure out that call is pregnancies. Okay, and this hue will be based on, so your color of the box plot will be based on the outcome. Okay, so if you go ahead and do this, you can label the x and y columns. You set plt.tight layout so that they appear together very well, and then plt.show. So now here, this should have come up. Yes, you can see in the same figure I have these now. Okay, so the first thing that you see here is the histogram, and on top of that you have the probability function, you have the distribution. Okay, as you can see that at least with respect to the distribution, there is quite a bit of overlap. Okay, pregnancies has quite a bit of overlap when it comes to the outcome 0 and outcome 1. The most important thing that I want you guys to notice here is that the 1, which is the diabetes section, comes under the 0, right? So there is a lot of overlap between these two. What this is basically telling you is that the distribution of 0 and the distribution of 1 does not have too much of a difference. There is a lot of overlap. So that means pregnancy might not be too much of a large contributing factor towards my contribution. Okay, This is what this plot is kind of trying to tell you. You'll see why I say this when you see with respect to some of the other plots. Okay, let's take a look at this violin slash box plot. This is the box plot. I did not plot a violin plot because at the end of the day, the violin or a box plot is the same thing, right? It gives you the same information. The violin plot looks like a violin, the box plot looks like a box. Okay, so as you all know, this is the box plot, and these are your intervals basically. So this is your 25th percentile, your median value, and your 50th percentile. Okay, so what this box plot is basically trying to tell you is that the mean value of the outcome one, which is the which is the diabetes individuals, right? For them, there is so they tend to be pregnant. Okay, diabetes individuals have quite a bit of pregnancy rate, high pregnancy rate, rather than healthy individuals, people don't who don't have diabetes. This is the first observation. The second observation is that out of all the individuals which don't have diabetes, the spread here is much smaller. Okay, so pregnancy, there is not as much variation with respect to pregnancy in people who don't have diabetes. However, there is quite a bit of variation, there is much larger variation with respect to pregnancy in people that don't have that people in people that have diabetes. Okay, the third observation you can make from here is that diabetes people who don't have diabetes with respect to pregnancies, this particular feature for people who don't have diabetes has two outliers. Okay, the box plot also gives you an idea about the outliers. So this is basically telling you that your data, your pregnancy data with respect to people who don't have diabetes have two outliers. Okay, so this is what these two plots are trying to tell you mostly. Now, let me ask you guys this. Do you guys get the general idea of what these two plots are trying to tell you? Can we please get a thumbs up if you understand the general idea? Because now what I will do is I will run these plots for each and every single one of them, and then we will see what it actually means. Okay, for some of these features, it will be a bit different. Okay, so we will actually see that, right? So people, do you understand? Only one of you gave me a thumbs up. Others? Okay. Thank you. Others, only 4 or 5 of you gave till now. Others, that Sasini, thank you. Manaswini. Okay. So most of you almost understand. Okay. Now let us do this particular plot for the next feature. Okay. So this time our feature is what? Glucose. Okay. So again, so if you think about it, subplot is not like this entire thing, right? This entire thing is your plt dot figure, right? When I say plt dot subplot, I am basically referring to the left hand side and the right hand side of this particular plot. Okay, that is why we have given the coordinates here. So this is 1 2 1, right? And if you think about it, this is 1 2 2. Okay, so that is why these are the coordinates. Okay, so this is the one is basically for the window that is in the first window. 2 1, that is the left, is going to be this particular plot, and 2 2, that is the right, is going to be this particular plot. It's just like that. Okay, so it is the same arguments everywhere. I'll simply go ahead and run these, and then we'll be able to see the plot on the figure. Okay, so now we have figure 2, which is with respect to this thing, which is with respect to glucose, right? So here you can see that glucose, there is quite a bit of portion which is actually not part of the overlap. Okay, there is quite a bit of portion which is not part of the overlap, and for the normal population, right, glucose follows a normal distribution, which is something that you would expect. This looks mostly like a normal distribution, right? So this is something you would expect. But for the diabetes population, it is kind of, it has two peaks, right? There are two peaks. One is people who have glucose around 125, and then there is people around, another peak around 175, right? So it is a bimodal distribution, and instead for the normal people, it is a unimodal distribution, it is a normal distribution, and there is quite a bit of portion of the glucose part, right, of the people who are diabetic, right, that does not fall under the normal distribution, that does not coincide with the normal distribution. So glucose might be actually a very good predicting variable of our outcome here, right, which is diabetes or not. Similarly, you can also see that people with diabetes have a median glucose level much higher than people without diabetes, which is something you would expect, right? The spread of glucose levels in diabetes is also slightly larger for people with diabetes, the spread of glucose level. And outlier wise, you can see that people with very high glucose levels are also present, but they are not diabetic. So within the normal non-diabetic people, there are several outliers here. And this is also something that is biologically valid, because at least personally, I know a lot of people who keep eating sweets and have very high blood glucose level, but have never been diagnosed with uh, diabetes mellitus, right? I don't know how that is possible, but yeah, this is something that has come up in research a lot. So also this is something that we can expect to see in our particular data. Okay, so this is about this particular feature, which is glucose, right? Now let us do it for the next one. So again, we will create the figure, and then we will click on step over to get the plots. So see, from this data, which is not too big, right, you can still get so much of information, right? So figure 3 is our blood pressure. Okay, now for blood pressure, you can see that these two, both of them form a normal distribution, right? Both of them form mostly a normal distribution. And the diabetic people, the distribution of the diabetic people is kind of coinciding mostly with the non-diabetic people, right? So that tells you something about blood pressure as a variable, that blood pressure as a variable is not really related to diabetic condition. Okay, your diabetes outcome does not really or your, rather I should say, your blood pressure does not really indicate, or does not really I should say correlate well with your diabetes outcome. Rather, it remains very similar in both cases. If you see, if you think about it, the mean here is somewhere around what, it's somewhere around 79-80, and the mean here is somewhere around 70-72. Okay, and that is absolutely fine. So I believe this is the diastolic blood pressure, because a systolic blood pressure of 70-72 is not good. So I believe this is the diastolic blood pressure. That is what they mean by this here. So let us go with that. Okay, in terms of the box plot as well, you can see that there is not too much of a difference outcome wise, whether they are diabetic or non-diabetic. It is mostly around the similar range. However, we do see there are some outliers. Okay, so that is something that we have to take note of. We are keeping note of this. Okay, next feature, let us go with the next feature. Okay, so we have figure 4 here. Now this is again skin thickness. So even for skin thickness, you can see that the distribution of the diabetic people falls completely within the distribution of the non-diabetic people. So this is also a very coinciding plot, not too much of a difference, right? Both of them. So skin thickness again is not too much of a contributing variable towards the diabetic outcome. Okay, a very similar response is also coming to us from the box plot, right? You can see that the level is kind of similar here, right? This is around what, 22, 23, right? This is 21.8, and this is around 27. Okay, so you can actually, if you take a look at the bottom right of my screen, you can actually see the XY coordinate. Okay, so you can figure out these values from here as well. And you see there is an outlier here, which is at 98.8 skin thickness. Okay, and they are part of the diabetes section. God knows what they were doing, but anyway. So we see that this guy also maybe not too much of a contributing power, because between these two outcomes, between diabetes and non-diabetes, not too much of a difference. The spread is also very much similar, and so is the median value. Okay. So again, this info, this particular feature, which is skin thickness, might not be as informative. Okay. So let us take a look at the next feature. Okay. This next feature is the insulin feature. Okay. As you can see, insulin also very, and this is very surprising to us, that we always associate insulin with diabetes, right? So people take insulin if they have diabetes, right? So insulin here also, it is not particularly associated with the outcome, because as you can see, the distribution of insulin, right, also coincides very well with that of the distribution of insulin with respect to non-diabetic people coincides very well with that of the diabetic people, right? And as you can see, even the modes are also pretty similar, right? So this is very similar, this particular mode here, again a little bit of a deviation but very similar. But you can see that insulin is not really affecting this a lot. A similar, very similar observation we are getting here as well. Although there is a much larger spread for the people with diabetes for insulin, the median is very much similar, right? For example, the median for non-diabetic people is around 42, while the median for the diabetic people, which is here, it's around what, it's around 1. So there is some difference but not a lot in terms of the insulin level. There are quite a few outliers with respect to the insulin, but one possible inference that I can draw from here is that the data that has been taken from people, right, this data did not come from people who are already taking insulin as a medication. Okay. Why do I say this? Because if people would have taken insulin as a medication, right, we would have seen a much larger shift in the distributions here, and also with respect to the blood glucose level distributions, right, which we did not see, right? We saw a very minor shift, right? And in insulin we are not even seeing any shift. So if people were already being administered insulin, there would have been some shifts here that we are not seeing. So probably this data is coming from people who are not on insulin as of yet. Probably this data was taken from people immediately after their diagnosis of diabetes. Okay, this is one inference we can draw from this particular plot. Okay, so there are 3 more features left. I will actually do all of this in one go, so that you guys don't have to wait through this entire thing again. What you can do is you can go to any line after the particular line that we have already done, right? Any line after where you want to finish. So I want to finish this entire for loop, so I will go outside this for loop to the next line, which is line X, and I will do a right click and then I will click on run to cursor. Okay, so let it run. So we have all the other plots here, right? Figure 6 is by with respect to BMI. Okay, again you see it is kind of very coinciding, both the diabetes and the non-diabetic ones. And that is actually something that has been proven recently in research, that BMI has very little to do with diabetes, right? You can have very similar BMIs with respect to a healthy person and still have diabetes. Okay, a similar thing has been observed here as well. Not too much of a difference here. It's around 30 and this one is around 34, not too much of a difference, right? Similarly, after BMI, we have this is the diabetes pedigree function. So the diabetes pedigree function also for some reason here is not too different, although there are a lot of outliers in the non-diabetic group, and maybe that is why we are seeing a lot of these similarities. Maybe that is why the modes are coinciding so well, because there are a lot of outliers, right? So all in all, from this data set, what we can kind of this is also by age. Okay, so again, kind of proof that diabetes is age agnostic, right? Usually not very prevalent with age, but however, there is some proposition here that okay, the median age of people with diabetes is around what? It's around 36, while the median age of people who don't have diabetes is around 27. So some form of difference is there, but not a lot, right? But all in all, if you think about it, a very key observation from all of these plots is that for most of them there were quite a few number of outliers in the non-diabetic people, right? So the non-diabetic group that we had around 500 data points, right? So a lot of those data points with respect to some of these features are actually outliers. Okay, I will close these plots so that we can move ahead, right? So a lot of these data points that we saw are actually outliers. So that is something that we have observed here. So do people understand the inferences and the interpretations I just made? Do you guys agree with what I say, or do you guys have any more observations that you made that I missed out on? Anything from you all? Yes, people, anything? So this is just me trying to tell you how you can do EDA. You can do so many more things, obviously. Uh, these are some of the just most basic things that I'm doing. You can also perform statistical tests, right? So since it is frequency based data, you can perform chi-square tests, right? So all of these things you can do. It's all about perspective. Some people want to look at visualizations and make inferences. Some people want to perform statistical tests. Some people do both. Okay. So do people agree with this up to here? Can I get a thumbs up if you guys agree with whatever inferences I have made? Okay, quite a few of you. Do any of you have any extra observations or inferences that you made and I kind of like mistook it or misread it or missed it completely? Anything, any pointers? Okay. With that said, then this is good enough EDA for us to make some judgments, to make some kind of informative decisions, right? So we did this with respect to this data set. In some of the next algorithms, we will be using another data set wherein we'll do this EDA again, and I will show you guys how EDA actually helps you decide so many things. Okay, so here again, this is a very simple data set, and most of the features are very well created, although there are some outliers, right? So from this EDA, although it gave you some interpretation and inference, you got to understand your data very well. It did not really help you a lot in terms of feature selection or engineering. Okay, you will still end up using all of these features. Okay, you don't need to remove anything. Okay, so the next step for us in this pipeline is to create the X and the Y matrix, obviously. So we have already created the features list. So all we have to do is pass that as an indexing strategy for the diabetes data frame. And we will have the feature matrix. As you can see here, this matrix or this data frame has all the features, but not the outcome variable. Okay. And the Y matrix is going to be nothing but our outcome variable, right? So this Y matrix is our outcome. This is whether the person has diabetes or not. The next step, as we discussed yesterday, is the train test split step, right? If I go ahead and run this line, you will have X train, X test, Y train, and Y test. You can always check them out here, and you can check how many there are. So there are 614 for training, and the rest will be there for testing, which would be around around 200 samples. So yeah, around 154 samples. Okay, so we have done an 80-20 split. Now let us build a very basic logistic regression model without doing any pre-processing. Okay, let us try what happens. So just like linear regression, we add the logistic we first load the logistic regression function into the model variable. Okay. Now we perform the training by using the fit function. So this is going to be the syntax for all the models. There will be a fit function to actually train the data. And for training, obviously you use X train and Y train, right? So if I go ahead and run this, model training has happened. See, it is telling me that you might also want to scale the data, refer to documentation for alternate solver. So it is giving me warnings. Okay, we have not done any pre-processing and it is giving me warnings. Okay, now let us do some predictions. Let us do the test using the X test, right? We all know why we don't give the Y test here, because this is an unseen part of the data that I want my model to predict. Now I have the X test. So these are the predictions that this model has made. Let us calculate the accuracy, confusion matrix, the F1 score, and the precision score. Okay, let us go ahead and do that. So in order to do that, obviously, I would have called the accuracy function, accuracy score function, confusion matrix function, F1 score function, and the precision score function. Okay. So here I have called it inside the print statement. The way you can call variables or functions inside the print statement is if you use an F string. This is known as an F string. Okay. You put an F before the inverted commas, and then you write whatever you need to write. And whenever you want to call a function or a variable, you put it inside curly braces. Okay. This dot 4F after the colon here basically tells to print the result. So it will calculate this, right? It will calculate this and it will print the result with 4 places after the decimal. Basically, that is what this guy does. Okay, so let me go ahead and run these lines quickly, and you can see that we have the following metrics. So we have an accuracy score of 0.7468, or we have 74.68% accuracy. Not too bad, decent enough accuracy. This is the confusion matrix. Okay, so we have 78 true positives, right? So true positives are what? True positives are the ones where the model has predicted diabetes and they actually are diabetic people. Okay, we also have 37 true negatives, right? True negative is what? True negative is where the model has predicted that they don't have diabetes, right? And they actually don't have diabetes. So you got this many correct. Okay, these two are the incorrect. Your 21 is what? 21 is your false negative. So people who are actually not, who are actually diabetic, but the model has predicted negative or not diabetic, right? And then 18 is your false positives, right? So your model has predicted that they are diabetic, but they are actually not diabetic. So your model has falsely predicted them as positive. So you got 39 of these wrong here. Okay, and 78 plus 37 of these correct. Okay, and the F1 score and precision score are also around 0.65, 0.63, not too great, not very close to 1. We want them as close to 1 as possible, right? Now let us try building this model again with some changes, with a few tweaks. Okay, first and foremost, what I will do is I will do some pre-processing. Okay, so we will pre-process using the min-max scaler today. Yesterday we used the standard scaler. Okay, today we will use the min-max scaler. Okay, this is nothing but a mean centering of the data. Okay, so all I have to do is first load the scalar function and then perform the scalar function on the training data set. Okay, I will go ahead and do this. Remember, you only scale your features. Okay, you only scale your features. Okay, again, when you are doing the fitting, right, when you are teaching your particular scalar to fit the data, right, you fit it only on your train, right, and then the transform. So this is where it learns the relationship of each of these variables. This is where it learns the relationship. It learns the formula that it has to use to normalize these variables or to scale these variables, right? Then the formula is applied when you perform dot transform. So you have to perform dot transform on both your train value and your test value. Okay. The training or the calculation of the formula to be used for scaling is done only on the training data set, right? Because if you do it on the testing data set as well, you are effectively giving testing data set information to your model. Okay, you are making you are making the testing data set very, very uniquely scaled for it to only work, right? In that scenario, what will happen is you will end up overfitting your model, you will end up overfitting your data. You don't want that. You want the inferences that are drawn from the training data set to also work for the testing data set. You don't want to draw any inferences from the testing data set as well. That is why you perform the fit only on the train, but then you transform both on test and train. Okay, so once you have done that, again, now I will use logistic regression, but this time I will use some other parameters. Okay, so the first parameter here that I am using is something known as a solver. So if you guys remember, I talked to you guys about the algorithm that is being used to figure out that best possible log likelihood line, right? So there are several algorithms which are available for us. Okay, if I go ahead and show you here on the documentation, right? So I will type in logistic regression sklearn, right? As you can see here, that with respect to the solver parameter, let me go there. With respect to the solver parameter, there are several algorithms available. There is something called LBFGS, there is something called liblinear, there is something called Newton CG, something called Newton Cholesky, etc., etc. Okay, so each of these algorithms, what they are for, what they work best with, are added here. Okay, with respect to that information, I am now trying it out with the liblinear solver. You don't have to go into how each of these algorithms work. That is not necessary. Just know there are several options available for you to experiment with. Okay. And this time I will also set a random state so that my results are reproducible. And I'm using another parameter called as penalty. So a penalty is nothing but you kind of giving a penalty to a feature if it is trying to outperform others. Okay, if a feature is dominating over others, you kind of bring down the weight of that feature. Okay, and this is to make sure that each and every feature, regardless of their scale, does not really kind of dominate over other features. Okay, so there are several forms of penalty available. What we are using right now is something known as the L1 penalty, wherein features that are not supposed to contribute a lot, right, that are anyways not going to be very informative, will have very low weights, so that other features which are supposed to contribute a lot will end up having high weights in order to compensate. Okay, so if we go ahead and run this now, I have loaded the logistic regression function with these parameters. Then we will again perform the training, right? So this line is repeated here, I don't know why. You guys can remove one of these lines. Okay, and then finally I will perform testing. Okay, so once I have tested, now here I have the predicted values. Now here, let me calculate the accuracy score, confusion matrix, precision score, and F1 score. For all of these, the input is the y test, which is your ground truth value, and the predicted values that you have just predicted. Okay, so if we go ahead and do this, you can see that now the accuracy score has gone up a little bit. We have gone up from 74.6 to 77.2, almost a 4%, almost a 3% increase in accuracy. Okay, so we have done somewhat better now. Okay, we have done somewhat better. Even in terms of the confusion matrix, we see that we have made 35 mistakes here, right? We had made 39 mistakes earlier. Our precision score and F1 score have also gone up a little bit closer to 1. Okay, so this is what pre-processing does. Pre-processing actually helps you make better decisions. Okay, so we can try out several things here. We can try out different things in terms of the solver here. For example, let me stop this. I will only take 5 more minutes, guys. Okay, we will do some experimenting now, and we can end here. After, in today's evening lecture, I will talk to you about the outlier reduction method. Okay, so let us actually try some other penalty. Let us try, there is another penalty known as an L2 penalty. Okay, let us try the L2 penalty once. Let's see what that gives us. So if I put a breakpoint here and I debug, okay, all those plots will again come up. Wait, let me stop this. So I don't want the plots to come up again. So I will comment this entire portion, and also these two plots. I only want to run the model now. Okay. And yes, now let us go ahead and hit debug. Let's see what we get. So see, as you can see here, with the L2 penalty, we have actually made one less mistake. Now we have made only 34 mistakes, right? And the accuracy is now 0.7792. Okay, it is now 0.7792. Again, a little bit better. Okay, if I use some other solver, say for example, LBFGS, for example, I believe that is a solver. Yes, where did that go? Yes, we have LBFGS. So that is kind of like the default solver that we used earlier as well. So if I do a rerun of this, let's see what that gets us. Okay, 0.7792, not too much of a difference. So the solver is not really making too much of a difference. Okay, liblinear or LBFGS. For the sake of it, let's try one more. Let's try. So here it says that Newton-Cholesky is a good choice if number of samples is much greater than the number of features times the number of classes. So the number of features is 8 times the number of classes is 216. The number of samples is around 700. So maybe this might work better. Let us try this. Let me go ahead, select this and copy. Paste it here. Let us actually rerun this and try. Let's see if this works well. So if you guys would have guessed by now already, these are what I mean when I say we are talking about hyperparameters. Your solver is a hyperparameter. Your penalty is a hyperparameter. These are parameters that are in your hand and you can choose what to use and what not to use. Okay, and that actually helps, right? So we will also talk about something known as hyperparameter tuning in one of the upcoming lectures and how you can do it. So right now I'm doing this manually for you guys. You can automate this entire process and I will show you how you can exactly do that. Okay, let's see here. It's 0.75, not the best. Okay, so basically the point of this entire exercise was to show you guys that these are some of the experiments that you will run when you are building a model. It's not only about just okay, we'll fit and then we'll predict, we'll get the scores and we'll report. No, try out different things and see which one is working best and then try to understand why that worked best. Okay, so that is going to be the goal for all of the machine learning algorithms that we do from now on. Okay, the rest of the part here is nothing but us trying to figure out some class imbalance issues and some we will try to basically remove the basically the outliers and stuff. So all of this we can take up during our next lecture. Okay, so we will begin our next lecture with this script where we will perform logistic regression again, but with certain few tweaks that will help us maybe improve accuracy or not. We don't know, we'll see. Those are experiments will run, followed by our class or our concepts on decision trees. Okay, so that is going to be the agenda for our evening lecture. I hope you all will join us, and for the evening lecture I would request you all please to join on time so that we can again I will try to finish by 7. I won't go beyond 7 for you guys. Okay, so thank you all for joining us today in this session. If you have any doubts with respect to the script that we ran till now or the theory about logistic regression, please feel free to raise your hand and ask. If you don't have any doubts, please give me a thumbs up.